Hi, my name is Jesse Thaler, and I'm recording this video from my office here at MIT. My apologies that I'm not there in Belgrade in person to tell you about this work, but Marcel Voss asked me to give you the case for jet substructure, telling you a little bit about the work that we've been doing at the Large Hadron Collider to study the substructure of jets, and maybe during Q&A we can talk a little bit more about the relevance of this work for a future lepton collider. Okay, so the focus of my talk today is on jets, and of course we've known about jets for 40 years. Since the 1970s, we've known that when you slam together particles at short distances, you make quarks and gluons, which then shower and fragment to form the collimated sprays of particles that we call jets. So here at the UA2 experiment from 1982, we find what I think is the first Lego plot of jets. And we see here one jet, two jet in this collision event, and again we interpret these jets as proxies for short distance quarks or gluons. So we've had almost 40 years to contemplate the physics of jets, so you might ask, well, what's new? Why are we still talking about jets in 2014? And I think we've had a bit of a QCD renaissance in the past 6 years or so. From 2008 to the present, we've had an explosion of new techniques for studying the properties of jets and studying QCD more generally. This renaissance has been driven by two different things. First, on the experimental side, we've had, of course, the Large Hadron Collider, which compared to previous machines has higher energy, higher luminosity, and for the purposes of jet substructure, finer segmentation, such that this intuitive picture that we have of protons colliding, making quarks or gluons at short distances, which shower and fragment to form sprays of hadrons, and then those sprays of hadrons are tracked in tracking and measured in calorimetry. This last stage, from the hadron level to the detector level, is more or less one-to-one, especially with techniques like CMS's particle flow. So on the experimental side, we've had enormous success in studying the properties of jets, mainly driven by detector advances. On the other side, on the theoretical side, we've had a variety of different types of progress in QCD. We've had new jet algorithms, most especially the anti-KT algorithm, and the development of anti-KT in 2008, that's the reason why I say that this QCD renaissance starts in around 2008, and as most of you know, essentially all jets at the LHC are actually anti-KT jets. We've also had an explosion of techniques to do higher order calculations, more loops, more legs, and also logarithmic resummation. I'm not going to talk very much about that in this talk. What I'm going to be focusing on is jet substructure, a field that probably also has its start in 2008, though there was some nice precursor work by Mike Seymour in the 1990s that anticipated some of the things I'm going to be talking about today. So the outline of my talk is as follows. I'm going to make for you the case for jet substructure. I'm going to start off by talking about the way that jet substructure has maximized the discovery potential of the LHC. Of course, one of the things we're excited about at the LHC is the possibility of discovering new physics, and I'm going to tell you a little bit about the way that jet substructure has enhanced those particular searches. Another thing that I'm particularly interested in is the way that jet substructure can enhance our understanding of QCD. That might seem a little bit strange, since the Lagrangian of QCD is of course very well known, but I'll tell you a little bit about how jet substructure measurements have inspired jet substructure calculations that have taught us surprising things about the structure of QCD. Just because of the limited time, I'm not going to tell you that much about the second aspect, and I'll focus most on the first aspect. Before I begin, I just want to encourage you to think about the relevance of what I'm talking about for a future lepton collider. Again, I'm going to be focusing on the LHC, but a lot of these techniques are directly applicable to a lepton collider. Okay, so let me start off with the first aspect of my talk, maximizing the discovery potential of the LHC using jet substructure. So here's a collision event from the LHC. This one was taken by the CMS experiment, which shows just a dijet event. One jet on one side, one jet on the other side, nothing particularly interesting about this collision event. Until you start looking at the substructure of this jet, and then you realize that, oh, actually, this jet on this side is composed of two subjets. This jet on this side looks like it's composed of three subjets. And if you look at the masses of the various subjets involved, you can actually convince yourself that this is not just a boring dijet event. This event is actually a boosted top event, where a top created with a large transverse momentum with respect to the beamline decays to a W and a bottom. The W then subsequently decays to two jets. And the whole system is so boosted that all of the decay products of the top are collimated together into a spray that's reconstructed as a single jet. You can convince yourself that this is actually a top quark by making a plot of the invariant mass distribution of jets that have this kind of three-pronged structure, and you see this beautiful peak at around 170 GeV, corresponding, of course, to the mass of a top quark. So this is a classic example of jet substructure, and I'm going to tell you a little bit more about how that's relevant for new physics searches. So maybe just to emphasize here, the reason why jet substructure comes about is because of the high energy of the LHC. And because of the high energy, this boosted regime is inevitable. So if you're doing some kind of new physics search for a heavy gauge boson Z prime decaying to TT bar, as the mass of this Z prime gets heavier and heavier and heavier and heavier, these tops get more and more and more and more boosted. And so whereas at low masses for the Z prime, down here, you can use a resolved search, where you can search for a top quark in the classic 3-jet final state. As you go to this boosted regime, there's a crossover where it's much more effective to look for a single jet that has 3-prong substructure. And in fact, as you go to even higher boosts, you start to run into issues with detector granularity, not even being able to resolve the 3-prong substructure of a top. So this is from a CMS search for a boosted Z prime, and you can see this nice crossover, where up to around a TeV, the tops are sufficiently not boosted such that you can resolve their decay products. Above 1 TeV, they start to get sufficiently boosted that you have to use jet substructure techniques. Already the exclusion is out to 2 TeV, which tells you that boosted techniques are going to be even more relevant as the LHC goes on 13 TeV running. Another reason why jet substructure is kind of inevitable is because of the high luminosity of the LHC. In particular, pileup is inevitable. So if you're looking for a boosted object like a top quark, whose actual invariant mass is close to 170 GeV, and you layer on a ton of secondary collision debris, you need some kind of jet substructure technique to disentangle this collision debris from the hard top quark that you're trying to resolve. And so from the simulation from Atlas, this is shown here, where a blue curve corresponds to the invariant mass of the top before you add pileup, and the subsequent curves correspond to the offset you get in the invariant mass distribution due to contamination from pileup. And using jet substructure techniques, for example, trimming that I developed with David Krohn and Lian-Tao Wang, you can kind of clean up your jet and come back to this beautiful 170 GeV peak coming from boosted tops. So high energy at the LHC, high luminosity at the LHC, and also high stakes at the LHC, where of course we're excited about searching for new physics. And this tells you that cleverness is inevitable. And again, since 2008, there's been this explosion of different techniques trying to exploit the substructure of jets and find evidence for new physics by using these new techniques. So I've just given you a very quick list of a bunch of things that have come out over this 6-year span. In the next slides, I'll just focus on 2 of them, angularities and n-subjettiness. But all these techniques are using the same core principles of jet substructure. You're trying to isolate prong-like behavior for boosted objects. You're trying to test radiation patterns, for example, to test quarks versus gluon jets. You're trying to use flavor tagging like B tagging to help give you even more information about where jets are coming from. And of course, this big issue of pileup mitigation, which I'm not going to say that much more about, but is very important for actually exploiting these techniques at high luminosity environments. Okay, so let me tell you a little bit more about these core principles of jet substructure, which are common to all these techniques, but I'll just show you how they work in a couple of key examples. So again, jets come from hadronic final states, and here are all the hadronic objects in the standard model. Of course, you have gluons, you have light quarks, you have B quarks, but then you have these heavier objects, WZs, Higgs, and tops, which we usually don't think of as being hadronic objects, but they have hadronic decays. And in the extreme boosted regime, these hadronic decays can be resolved as a single object that has either 2 or 3-prong substructure. And so we want to develop new jet substructure techniques to help disentangle ordinary jets from these boosted objects. So the first thing we want to do is find new discriminant variables to tell the difference between n-prong jets and 1-prong jets. So here are 2 jets, one from a boosted top, one from an ordinary quark or gluon jet. Both of these jets have the same invariant mass, around 170 GeV, but just from the color coding you can say that clearly this boosted top really has 3-prong substructure, whereas if you try to color code this QCD jet, you really can't see 3 prongs. Maybe you can get some colors, it doesn't really work very well. Of course, by eye, we can tell n-prong versus 1-prong very well, but we also want to have equations or formulas or observables that allow us to distinguish n-prong versus 1-prong. And one that I developed with a former MIT undergraduate student, Ken Van Tilburg, is called n-subjettiness, and true to its name, it's an observable that tests whether a jet has n-prongs. I'm not going to tell you very much about how this observable works in detail, but just to say that this observable is infrared and collinear safe. It's built out of summing the transverse momentum of all the particles within the jet, measuring the distance of particles to candidate subjet axes, and raising things to an arbitrary angular exponent beta. And in particular, ratios of n subjettinesses are very useful for boosted top or boosted Higgs W or Z identification, where for boosted tops, for example, you want to say how 3 subjetti is a jet compared to how 2 subjetti is a jet. And this ratio gives you this nice separation between top jets, which are more 3-prong than 2-prong, versus QCD jets, which don't really have any prong-like structure. And so by making a cut on this tau 3 over tau 2 ratio, you can get a nice separation between top and QCD. So n-prong versus 1-prong, that's one of the pillars of jet substructure. Another pillar of jet substructure is quark-like versus gluon-like radiation patterns. So gluons have a color factor of 3, so they have more copious soft radiation around them. Quarks have a color factor of 4/3, so their radiation pattern is more sparse. Of course, you want to tell gluons apart from light quarks. And also, these heavy objects, WZ, Higgs, and top, they actually have more quark-like objects in the final state. And so you can use radiation patterns to tell those apart. So one nice jet substructure observable for separating quark-like versus gluon-like jets apart are called angularities. They were originally developed in 2000s in an E+ E- environment just to test the properties of QCD itself, but they've turned out to be fairly effective for separating quark-like versus gluon-like. For example, if I take this angular exponent beta to be 1, that's an observable that's known as jet width. And you see this nice separation between quarks, which have a smaller jet width, versus gluons, which have a larger jet width. And by making a cut here, you can separate quarks from gluons. Also shown on this plot are different Parton-Schauer Monte Carlo programs, Pythia here and Herwig, and you can see there's actually interesting differences between these two programs. And one of the goals of jet substructure is to perform measurements to help understand to the degree to which one model of parton showering versus another model of parton showering is more realistic compared to jets that we actually see at the LHC. Finally, let me mention flavor tagging as one key element of jet substructure. And this one has really been developed on the experimental side. And in this jet, you see something that if you didn't know what you were looking for, you would look at and say, oh, this is dijets. Then you look inside this jet and you say, oh, this jet actually has 2 prongs. And then you look inside those prongs and you see that those 2 prongs actually have displaced vertices. And so this is evidence for a jet that actually has 2 B mesons in it. And with these 2 B mesons, you can infer that this is actually a boosted Higgs event, or at least a candidate for a boosted Higgs event, where you have some heavy object decaying to BB bar. And because of the large boost, these BB bar are actually coincident. And you have to develop new subjet B tagging methods in order to exploit this particular final state. So putting together all of these features, we've actually had a boon for new physics searches using jet substructure. Just to give you one example from Atlas in a heavy search for W primes. W primes in this case are hypothetical objects that decay to a top and a bottom. And using a combination of trimming for pilot mitigation, B tagging, which appears in this both from the B jet that you see in one of the W prime decay products, but also the B subjet coming from the top decay product. And then these substructure variables, KT splitting scales, and n subjettiness. In particular for n subjettiness, by making a cut on tau 3 over tau 2, you can get this nice separation between yellow, which is the multijet background, and these empty histograms, which are the signal. Similarly, you can make a cut on tau 2 over tau 1. And in this final state of W prime going to top B, the top going to WB, and the W going to QQ bar, you have a QQ bar, BB bar final state, and you can search for this hypothetical W prime. And you can see that using these jet substructure techniques, we already have sensitivity to, in this case, 1.7 TeV W primes. And of course, as we go to higher energies still, we're going to be able to exploit these jet substructure techniques further and increase the reach that we can have for new physics searches. And you can imagine applying these same type of techniques at a future lepton collider. So in my remaining time, I want to tell you a little bit about the way that jet substructure techniques, in particular analytic approaches to jet substructure, have enhanced our understanding of QCD. So I'm going to be a little bit brief on this point. I have a couple of extra slides in my backup slides to tell you about other examples. So one of the exciting things about the jet substructure community is that new jet substructure techniques have inspired new analytic approaches. So I told you already about the jet trimming approach to trying to mitigate pileup. In the original BDRS paper from 2008, there was another approach to mitigating pileup called mass drop, which takes a jet and declusters it until it finds 2 hard subjets, in the process removing radiation that's most likely associated with pileup contamination. And in this wonderful paper by Dasgupta, Fregeso, Marzani, and Salam, they did the first analytic calculations of these pileup mitigation methods to try to figure out what extent there was collateral damage on the jet. That is, how did you change the original jet radiation pattern by applying these techniques? So in the case of trimming, they found something interesting. Trimming has two parameters, and not surprisingly, there's two transition points in the trimmed jet mass distribution. Amazingly, this mass drop procedure, or at least the modified version of that mass drop procedure, actually has only one transition point. And in contrast to the expected Sudakov double log behavior, this upside-down parabola on a log-log plot, what was found here are single log behavior, where you have just this straight line behavior, something that I'd never seen before in a jet substructure observable. So that's really interesting analytic behavior, and we wanted to understand better this transition between Sudakov double log structure and this single log structure. So we developed a new technique called soft drop. This was work I did with Andrew Lakowski, Simona Marzani, and Gregor Soye, where we interpolate between applying no pilot mitigation and then applying the pilot mitigation strategy of mass drop. And what you can see is that if I apply no pilot mitigation, I get this characteristic Sudakov double log peak. And then as I dial this beta parameter down, 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 down to the mass drop regime, I see this flattening out of the distribution. You can even go to negative values of beta and see this sharp turnoff behavior in the soft drop jet mass distribution. So we introduced soft drop mainly to try to understand how this mass drop procedure was working, but the feedback loop in the jet substructure community has really been fantastic. And recently CMS actually did a W tagging study using soft drop to isolate boosted Ws. And so this feedback between these communities is really fantastic, with new techniques inspiring new analytics, inspiring new techniques, inspiring measurements, and I'm excited to see this feedback loop continue in the future. So to summarize my talk, today I've tried to give you the case for jet substructure, and the case for jet substructure is actually rather simple. It's the exceptional LHC performance in terms of its fine segmentation, the extreme kinematics that you get in the boosted regime, the challenge of jet contamination that you get at high luminosity, and the excitement about searching for physics in and beyond the standard model that has made jet substructure such an exciting thing at the LHC, and something that I hope will be adopted in a future collider. I've tried to tell you a little bit about how jet substructure techniques have maximized the discovery potential of the LHC by using creative analysis strategies for hadronic final states. And hadronic final states, of course, are going to be present no matter whether you're at a hadron collider or at a lepton collider. That's why I think these techniques that we've developed for the LHC would be relevant for a future lepton collider. And finally, I've given you a little bit of a teaser in the way that jet substructure has enhanced our understanding of QCD. We've obtained new analytic results in perturbative and non-perturbative field theory inspired by all of this jet substructure work. Well, it's been a pleasure telling you about jet substructure today. I'm sorry I'm not there in Belgrade to answer your questions in person, but hopefully we'll get the video link set up for the Q&A session. Thank you very much.